Hello, grade 9. How are you today? I hope you all are safe and well. Today our lesson about hot and cold. So what we should know about hot or cold, okay? In our life, we know that the thermal energy could be hot or cold, especially hot, like something hot. But what about the coldness, okay? How can the energy transfer, or the process of transferring this energy, or how can we say this thing is cold? Okay, so please grab your highlighter and let's explain more about the lesson. Hot and cold, thermal images. So in this picture you have thermal image. Okay, shows that a scorpion, someone is holding a scorpion. Okay, and we can see the person is look in red and orange, and the scorpion is in blue. So why these two different colors? Okay, a scorpion is cold-blooded animal. This is a good information. It's not hot blooded or warm-blooded, and the person holding it is warm-blooded. You cannot tell the temperature of the scorpion or the person by looking at them. So if I just look at you and see everyone, I cannot just guess your temperature, okay? Because this is something we need to measure. We cannot just see it. So here the image of the scorpion is taken with special camera. This special camera produces thermal image, okay, that shows the differences in temperatures. So here with this blue, that means it's cold. Okay, if you look at this scale here, you can find the temperatures. Okay, here about 90, 85, 80, 75, 74.9. So the scorpion, maybe it's like 74 or 74 and a half, 74.9. Okay, and the person is more than this. Okay, something like glowing. We all know that if we want to represent something with thermal, that means like something is hot, we need to use the color red, or that means something is glowing from the temperature or the heat. Okay, so what's the difference between the temperature and the energy? We all know the meaning of thermal energy, but is it the same with the temperature or not? So the temperature tells us how hot or cold something is just by measuring it. Okay, and we use thermometer to measure the temperature. A liquid inside a very narrow glass tube expands when it's heated. We have very simple example in our houses. We have the thermometer, the liquid thermometer. We have it even in our lab. Okay, we have the liquid thermometer. It's inside the thermometer there is a very narrow tube that full of liquid. Okay, this liquid can expand when it's heated. When the temperature is rising, this liquid will expand and gives us the right temperature, the correct temperature of anything, of the liquid, of the body, of the temperature of anything. For a long time, thermometers were made using liquid mercury, the silver material that we can find in thermometers. But we all know that mercury is poisonous. So instead they are using another liquid of it, which is from another liquid in it, which is alcohol, because alcohol can expand if it exposed to heat. So mercury is poisonous. So today the liquid used in thermometers is alcohol. Digital thermometers do not use liquid. Instead, they use a sensor to measure the temperature. So here we have some kinds of digital thermometers. These digitals, they are using sensors inside them to measure the temperature, not liquid, but the ordinary one or the normal one that we are using in our houses or in the lab, we're using the liquid one and sometimes the digital one. So what's the unit that we measure the temperature with? We use temperature the degrees Celsius, which is this sign, okay? Human body temperature is 37 degrees Celsius. Some countries, they are using the unit called Fahrenheit, okay? But we are using degrees Celsius. The coldest temperature ever recorded on Earth was minus 89.2 Celsius in Antarctica in 1983, and the hottest temperature ever recorded was 56.7 degrees Celsius in Death Valley, USA in 1913. So when we heat up a substance such as water, its temperature rises. We transfer energy from a chemical store of a fuel such as gas to the thermal store of energy in water. Thermal energy and temperature are not the same. So here, when we use something like fuel, any source of energy, fuel, gas, liquid gas, fuel like solid or any kind of fuel that give us energy, thermal energy, okay? Here the thermal energy will transfer where exactly, or from where to where? First, from the chemical store of fuel, whether if this fuel is gas or liquid or solid. Why we said chemical? Because the reaction, which is the combustion reaction, this is chemical. This is happening because of the reaction of these chemicals together. So this is chemical. From the chemical here will transfer to the thermal store of energy inside the substance that we are using, okay, that we are heating. So this substance that we are heating will store a thermal energy. In this case, the temperature will increase. So here, the temperature and the thermal energy are not the same. The temperature is just measuring, okay, just measurement of, or measuring of the degree of how cold or how hot this substance is become or is. So here, for example, if we have a cup of warm water and swimming pool can have exactly the same temperature. So sometimes if we have just a swimming pool and we took this water from it in a cup, both temperatures are the same in the cup and inside the swimming pool. However, the swimming pool stores much more thermal energy than the water in the cup. So why? Because of the size, okay? Because of the size can store more thermal energy. So how can this happen? Okay, let's imagine together if we start to heat this water, the swimming pool water, we need more thermal energy to warm it up, okay? And we need less thermal energy to warm the water inside the cup. So here, if we want to, if we left these two specimens, let's samples, I say samples, not sorry about specimens, if we left these two samples to cool down, okay? So who's going to lose the thermal energy first? Of course the cup, because the cup have less thermal energy than the water in the pool. So unlike thermal energy, temperature doesn't depend on the amount of material. So here, the temperature could be the same. It doesn't depend on the amount of the water or amount of the size of the cup, because the size of the cup the water inside the cup have the same temperature of the swimming pool water, but they do not store the same amount of thermal energy. So in this case, temperature doesn't depend on the amount of material. Heating solids, liquids, and gases. Okay, when we heat solids or liquids or gases, what's the thing that change inside them, or what makes them hot, or how this thermal energy can transfer? So let's see together. The process of heating changes the motion of the particles. It's like someone is standing in raw, and someone else, they are moving. For example, they are moving in slow speed, okay, slow motion, and someone came with a fire and coming near to them. This can make the raw change the speed, accelerate or speed up, okay? So this is the same thing here. When you heat solid, liquid, or gases, you are changing the motion of the particles inside them. So if it's solid, the particles will vibrate, because we know that the particles do not move inside the solids because they don't have spaces. About the solid liquids, they will start to move more and more. In the gas, they will find a way to escape. So here, if you heat a solid, the particles in the solid vibrate more. In liquids and gases, the particles move faster. The temperature has increased. So here, when you heat something, that means you are giving it thermal energy. Okay, you are transferring thermal energy to a material. So when you're transferring this thermal energy, you are changing the motion of the particles. In this case, the temperature will increase. You cannot say that the individual particles in solid, liquid, or gas get hotter. Each particle can only move or vibrate faster. Temperature of a solid is a property of the solid, not the individual atoms or molecules that make up the solid. So each material has properties of molecules, or have different atoms, okay? Different atoms, like from the wood, to the wood, for the iron, to the glass, okay? Each one of them is different. But here we cannot say that each particle or these particles are getting hotter. No, because this temperature of this solid, it's only a property of a solid. Only a property of a solid, not the property of the atoms. Okay, it's not the property of the atoms. So we cannot say about like how much it's getting, like how much cold or hot is it. Okay, because we are just trying to move or to change the motion, only to move the particles or vibrate the particles. So here in the solid, they are in a regular pattern, so they are vibrating. Now, trying to break the pattern. In liquid, they are moving. The particles in gas also are moving. So how much energy does it take to raise the temperature of an object? So do we know how much energy we should give to raise the temperature or not? So this amount, or the amount of energy that we need to raise the temperature of any object, depends on three things. From material to material, it's different, okay? Depending on these three things. The first thing is the mass of an object. The mass of the object. If it's big mass, small mass, or what exactly. Also, what it is made of. The material also can differ from the temperature can differ. The thermal energy can differ from one material to another. Third thing is the temperature change that you want. So, do I want to change the temperature too much, or do I need it to be the same, or decrease it, or what exactly? So let's see step by step. Let's see the first point, the mass of the object. So how can the mass of the object can so how the energy can depend on the mass? In greater mass there are more particles. You need to transfer more energy to get them all moving or vibrating faster. So let's have a very simple example about this. When we studied about particles before, we were acting that we are the particles, okay? And we were acting that we are solid particles or liquid or gas. So let's say if we have like someone is skinny, okay, and someone is chubby, okay, or another one with like more weight or like bigger weight. So if I am the thermal energy, or if I am the energy, I can move the skinny one faster or easier than the fat one or the big mass one, okay, and vice versa. It's hard for me, or I need more effort just to make that that one moving, or at least just shake it or vibrate it, make it like just like swing, okay? So this is the same thing in thermal energy. If I have a block of wood, okay, and I want to burn it, and in my other hand I have a very small piece of wood, a stick, let's say stick, okay, I can burn this stick using a lighter, but I need more thermal energy, a fire, a big fire, an oven, anything just to burn that block of wood, okay, because the mass is different. So the greater mass, the more particles we have inside it, so that means more energy is needed to get them move or vibrate. All of them like vibrate. Okay, what about the material? The particles in different materials have different masses. If the particles are more massive, you need more energy to get them move or vibrate faster. Okay, do we have any example? Let's think about iron, and let's think about iron and glass, okay? If the mass, if the part of the particles are different, I need different thermal energies to make them melt. That means make them vibrate, make the particles inside them vibrate more and more and more until I melt them, okay? So different materials have different masses. So this is the reason, because these different materials, they have different masses, the particles have different masses inside them. So if the particles are massive, that means like we can say like heavier, okay, or more dense, that means more energy is needed to make them move or vibrate. Okay, what about the temperature change that we want? For a bigger temperature change, you need to get the particles all moving or vibrating even faster. This takes more energy. So if I want to increase the temperature, okay, if I want to if I want the temperature to raise very quickly, that means I need the particles to move faster and faster. How can I do this? I need to increase the thermal energy. I need to give it more energy just to make it hot enough for me. Okay, hot to cold. Thermal energy always moves from hot object to cold object. So we said before, if we have a piece of or an ice cube in our hands, after minutes it will start to melt. Why? The energy didn't leave the ice cube, but the energy from our hands got inside the cube. So always the thermal energy moves from hot objects like our hands, which is like warm, or we can say hot in compare with the ice cube, okay, to the cold objects, which is the ice cube here. So if you put a cold object in contact with hot object, the temperature of the cold object will increase. In this case, the ice cube will melt. And the temperature of the hot object will decrease. Also, we can notice that our hand is getting colder and colder. Thermal energy has been transferred. So thermal energy is transferring from hot object to cold object. Look at the ice cubes in a glass of water. Thermal energy will be transferred from the hot to the from the water to the ice, and it will melt. If you put a hot pan in a sink of water, the water will get hotter. Thermal energy will be transferred from the pan to the water. Eventually, the pan and water will end up at the same temperature. So if we have a hot pan, okay, if we have a hot pan, how can we make it cool? Okay, if we put it inside the water or under the water, here the temperature or the thermal energy from the pan will transfer to the water. In this case, both of them will be at the same temperature. So now let's take a look over the summary of the lesson. Hot and cold. Temperature is a measure of how hot something is, and measured in degrees Celsius. Thermometers are used to measure temperatures. Temperature is independent of mass. When you heat up solid, liquid, or gas, the motion of the particles change. So this was all about hot and cold. If you have any question, please write it down, and don't forget the yellow box as a homework. Okay, I hope to see you soon, safe and well. See you next time. Bye bye.